Good evening for those of you in Europe. Good afternoon, I suppose, to those who are in America. I'm going to be basing my lectures broadly on the material which I've distributed as the lecture notes. There may at points be stages where I throw in additional material that I have either prepared later or thought was necessary. And that will be the case in this lecture. There will be some material that's not in the lecture notes. So I'm starting out with a talk about Turing. Let's shift to put the screen sharing on. As I say, I'm starting out with a talk about Turing, and it'll be relatively introductory, but we'll focus on aspects that if I were teaching it to computer science students, I wouldn't focus on so much. It'll focus on the more philosophical implications of what he was doing, rather than the technicalities of what he was doing. So the outline of this is I'm going to talk about the process whereby people stopped thinking of logic in terms of reason and moved to a process of talking of logic in terms of a formalism. I will then talk about what Turing thought Marx to be, maths to be, which the Turingist conception of maths is one that my colleague Greg Michelson and I pursue strongly in our publications, that maths is a material process, and Turing cataloged or specified that for the first time in a very clear way. And he did that by means of his hypothetical machine, the Turing machine. The Turing machine was invented as a thought experiment in order to solve an outstanding problem in mathematical logic, the decision problem. And I will therefore touch on the halting problem, which was the way Turing refocused or rephased that concept in mathematical logic. At that point, I will go across to new material that is not included in these notes and spend some time talking about why the digital character of the Turing machine is important and what implications that has for a materialist conception of the world. I'll then show that although it might appear something relatively separate, the work which Turing did during the war on code breaking is related to that. And very briefly, I will talk about his idea that machines could think, or could in principle think. Now, the classical view saw reasoning as a faculty, something that humans could do, or that the human psyche or soul could do. And it was the presence of reason in humans that distinguished us from animals. And there were recognized to be rules for correct reasoning, and Aristotle is the most obvious person who laid these down. And it was held that reasoning was something could be taught. So reasoning was seen as something inseparable from the nature of humans and something which distinguished humans from everything else, though it was hypothesized that the gods might reason as well. Now, reason was still was thought of as something to do with thought. And the transition point comes with the Irish mathematician Boole in the 19th century, who published his book, The Laws of Thought. And it's rather surprising if you come to the laws of thought as a computer scientist, because you expect it just to be on what we now know as Boolean algebra. But the title says what he thought it was. It was how he thought processes actually had to operate, how he believed thought processes had to operate. And he believed essentially that they operated in what later 19th century logicians would call set theory. So his Boolean logic was a logic of essentially of predicates and sets. But his innovation was to show that these could be treated mathematically. He says, let's conceive of an algebra where the symbols x, y, z, etc., admitted indifferently the values 0 and 1. And these values alone. The laws, the axioms, and the processes of such an algebra will be identical in their whole extent with the laws, axioms, and processes of an algebra of logic. So he's establishing an equivalence between what had previously been seen as two distinct disciplines, that of logic and thought, and that of arithmetic. And of course, the logic he invented, the Boolean logic, is the basis of all modern computing and all data processing subsequently. So insofar as correct ideas are proven by practice, he clearly had the correct ideas. There's a mistake in this. Basically, he's saying true is 1, false 0, and is equivalent to a multiplication, and or is a variant of plus. My mistake is saying 1 plus 0 is 0. It should be 1 plus 0 is 1, obviously. It's modular arithmetic because he says that 1 plus 1 is 1. So it's arithmetic of a bounded or what we would now call saturating arithmetic, that it can't go above a certain value. During the 19th century, starting on from Boole, techniques were developed to express any logical proposition in terms of an algebraic or mathematical formalism. So you can say for all A, for all B, A or B is equivalent to not A or not B. And this means that within the context of formalism, reasoning then became the same as manipulation of symbols, a form of calculation. And this is something that Leibniz had alluded to as a possibility, but didn't in fact himself push it very far. The Jevons, who's best known as an economist, actually developed what he called a logical piano, which was an electrical device for logical arguments. So from the formalization of it in the 19th century, people very rapidly started to move to trying to think, how could we turn this into a mechanism? So we have a formalist project. A formalist project started with Boole, and something which seemed to be very powerful. And therefore, it started to be seen as a potential basis for mathematics in general. Boole was saying, okay, we can form logic on arithmetic, but then the question is raised, could we in fact do it the other way around? Could we establish arithmetic and all branches of mathematics on logic? So that this is Russell's project. And could you use logic to, firstly, could you found all mathematics on logic? And secondly, could you use logic to deduce any true mathematical proposition? And a third variant of that is to say, can the truth or falsehood of any mathematical problem be determined by purely formal means? And this was Hilbert's problem, Hilbert's decision problem, posed in 1928. And there is a slight ambiguity of what he means by formal or mechanical means. He's talking about someone who does arithmetic doing essentially purely mechanical work, one which didn't require any deep thought. The simple application of rules that they've learned. So he's asking, can the truth or falsehood of any mathematical proposition be determined by a simple finite set of rules of deduction and inference? So that's the problem, the context in which this is posed. It's worth looking at what people meant by mechanical in the late 19th, early 20th century. For instance, you're probably familiar with the opposition that Engels expresses to mechanical materialism and says dialectical materialism is something better than this. But that opposition to what was seen as mechanical was widespread in continental or German thought, due to the influence, I think, of Marx particularly, but it was based in a long-standing dispute about whether the mechanical theory or mechanical concept of the world, which was seen as the concept put forward by people like Thomson and Maxwell, whether this mechanical concept of the world was adequate, or you needed something beyond a mechanical concept of the world. Now, this came to a big crisis in the first years of the 20th century. And in the context it was originally posed, which was the context of physics and the context of the theory of heat, it was resolved by Einstein. But the negative connotations of mechanical continued. And here we see it being posed by Hilbert some 20 years after Einstein resolved the argument in favor of the mechanical philosophy. So what Turing did is he showed there's no solution to Hilbert's decision problem. And to do this, he developed the idea of the universal computer. And in doing so, this conceptual innovation has totally transformed how we understand computation and reasoning in the period after that. The results were not immediate, but by the 1950s, they were very evident. And he did all this at the age of only 24. For this, you can look at the Essential Turing, chapter 1. In order to understand what he did, we have to look at how he defined what maths was about. He said that human mathematicians are limited. They are only capable of observing a few symbols at once. And this is obviously the case. You can't take in an entire sheet of paper full of maths symbols. You have to focus in on a small part of a formula. You have to focus in on a few figures if you're doing arithmetic calculations. He also says people have a limited internal memory or state of mind. There are lots of psychological experiments which test how long a string of digits a person can be told and accurately repeat. And it's quite short, maybe 7 digits or so. So our buffer of, well, using post-Turing terms, our buffer of symbols that we can operate on is quite small. So both of those are undoubtedly correct statements about human potentialities and human abilities. He also says that any mathematician or any school child has a learned set of tricks and rules of thumb, which are inculcated in the school child when they learn their times tables. They're inculcated in the older student as they learn a set of standardized formula for integrals, etc. And this is most important. He says, mathematician must be assumed to have a pencil and paper to write things down. Because unless you have that, you're limited to what you can do by mental arithmetic, which is not so great. Obviously, there are some autistic prodigies who could perform prodigiously long multiplications in their head, but this is very rare. And in general, that's not the basis that people work with. So what's his idea of maths? He starts off essentially from the idea of the maths you're taught at school, where you have squared paper and you write figures on the squares. So if you want to, you're taught at school, if you want to add 13 to 28, you put them in squares, underline them, and you add 3 and 8. And that's a learned rule of thumb. The learned rule of thumb that you're taught in the second year of primary school, that 3 plus 8 is 11. You just have to say 3 plus 8 and the answer comes out in your mind. It's been inculcated into you. You're then taught a rule for how to write these down on the piece of paper. You write a 1 underneath the line and you write another 1 at the top of the second column. You can then repeat the process. Now remember, we only looked at 2 symbols. We looked at 2 symbols and our mind came up with the answer. So you now look at another 2 symbols, the mind comes up with the answer 2. We don't bother to write that down because we can remember one number like that. We look at the next symbol, 2 plus 2 is 4. We write that down. So this is what he says is the essence of what people doing mathematics are. And it's the same if you're talking about algebra. So we start off with an initial formula, x into a plus b. The first state of the transformation is an internal state of mind where you remember that you're multiplying by x and that you've read the letter A. So you write XA. You then copy the plus. Looking up, you copy the plus. You then read B and you still remember that you're dealing with X. So you can write XA plus XB. At each stage, you only remember a little and you keep looking at the formula to deduce the next thing to do. Now, all this is obvious, but it was so obvious that mathematicians didn't really remark on it. These limitations of the human mind were not noticed. And there tended to be an exaggerated idea of what the human mind was capable of, even though the actual atomic steps that mathematicians were doing were as simple as this. So he reasoned that if in principle you could build a machine that could detect a small number of symbols at a time, that could have a finite internal memory or state corresponding to this, the finite number of states of mind, which he said any mathematician works with, and have a set of rules of thumb, which he said you can write down these rules of thumb in a table in the read-only memory of this machine. And finally, the machine must have something equivalent to the pencil and paper, which is a read-write memory to record the calculations as they go along. He argued that if you had such a machine, it could do all that a mathematician could do. And if you could prove that there were limits to what such a machine could do, there were no steps that a human mathematician can carry out that weren't already included here. So a proof about what the machine could do was also a proof about what the mathematician could do. And in fact, if you build computing machines, you very rapidly build ones that can do all these calculations far faster and more reliably than a human mathematician. Now, his first machine was hypothetical, and he didn't actually build it, but it's not inherently hypothetical. People have subsequently, for didactic purposes, built replicas of the machine he proposed. And this is a recent practical implication. Notice what it's using. It's using a reel of 35mm film, clear film. It has a mechanism here for writing and reading symbols, and there are motors which can move the tape backwards and forwards and have it reeled on or off onto one of these reels. Now, that looks a real Heath Robinson sort of machine, but it remains canonical because it's one of the simplest models of a general purpose computing machine. So let's look at it in more detail here. You've got two motors, one which moves the film back and forth, and another motor which can bring a print head into position. The print head can either have an eraser or a inked part of a roller. And there is an electric eye which can inspect the film. And all, Turing simplified the whole set of symbols that mathematicians use to just a mark or no mark, a 1 or 0 in Boolean terms. So you've either got marked squares or blank squares. And his argument was, this is general enough since it was already well established that you could have a numerical system other than decimal, so binary number systems were well established. It's relatively fanciful, this mechanical thing, but you have a program which you have a set of possible current states, current state A, B, C, etc. For each current state, it has an action depending on whether the current symbol under the head is 0 or 1. And the actions are composed of three things: what symbol you write, whether you move the tape left or right, and what the next state you go to. Now, that simple set of rules has been well established as being adequate for general purpose computing. And in a simpler way, or sorry, in a more complicated way, if you look inside any modern microprocessor, you find something equivalent to this table of rules. It would be called the microcode or the program logic array. And you have something equivalent to the tape, which is the random access memory. Making it random access speeds everything up, but doesn't change the basic principle. So the conceptual model he presented was, you've got a set of rules in your read-only memory. You've got a head which can traverse the tape, and you feed into it a program followed by data. Now, this is important because he showed that you can have a general purpose or universal program in the rules table, such that it can interpret any other program, including interpreting a program which is equivalent to itself. And this ability of a computer to emulate another computer was hypothesized by Turing right back in 1936, and is a standard theme of computer science ever since then, so that nowadays you can have people on a modern PC, and the modern PC can emulate another model of computer, an old Atari computer from the 1980s, and can then run the games from the old Atari computer. But in doing that, they are just applying this principle of general purpose emulation. And what Turing was saying is, once you reach a certain complexity in your rules table, then you can emulate any other machine, including yourself. And he proved this by exhibiting a particular machine which was capable of emulating itself or any other machine. Basically, it could emulate something which started off with a set of rules and then had data. And this idea, or this model of computation, was the model of computation which dominated 1950s computing. 1950s computing machines held most of their data on tape. They had a relatively small table-driven set of operations in internal memory, and the data processing occurred between the tapes. Now, there's soon developed a theory of multiple tape Turing machines to handle more complicated problems, but this actually was how commercial data processing worked. And instead of using paper tape with an eraser, they use magnetic tape, which is much easier to erase. But that the same essential principle was being applied. Turing never actually built a machine of that type. He did, by the 1940s, start working on a machine, and his machine is in the Science Museum in London. And instead of tape, he actually used mercury delay lines to store the information. By modern standards, it's a very odd and ultra simplified instruction set machine. Those of you familiar with assembly language programming, it's essentially a machine which has only got move instructions, which can move data between arithmetic units or between areas of memory, and everything is a move instruction, which is just about the most minimal basic table you could have. And his machine, with just these move instructions, was capable of general purpose computation. The mercury delay lines were widely used in the 1940s, early 50s as a way of storing information. Basically, you stored the information as acoustic waves. Now, how does this relate to reasoning and proof? Well, it's clear nowadays that any system of mathematical rules or axioms can, in principle, be written as a computer program. And a computer program can equally be thought of as a particular set of rules or axioms. And what he says is, Hilbert is concerned as to whether a particular axiomatic system is adequate to prove theorems by purely mechanical application. Well, we have the purely mechanical application in our rules system, and we want to, in our general purpose universal computer, universal set of rules. We want to feed it with a particular set of axioms and then a theorem. And we want to say, can those set of axioms be used to prove the theorem? So the decision problem amounts to whether the axioms will halt on the theorem. And cast in computing terms, will a particular program, the program that is this set of axioms, halt on a theorem? Because there's always the possibility that the computer will never stop. It may go around into infinite loops. And we want to say, can we show that a computer, given the axioms and a theorem, will halt with a true or false answer? So this is one level up from applying the axioms to the theorem. We're making a meta statement about, can we show that the whole computer, given the axioms and the theorem, will halt with a true or false answer? Because if we can show that it will halt with a true or false answer for any set of axioms, then Hilbert's conjecture would have been proven. What Turing showed was that it's impossible to have a general procedure for showing if another program will halt. You can't have one program which will prove whether or not a second program will halt in all circumstances. Because he'd previously established that axiomatic systems and programs were equivalent, it follows that the decision problem set by Hilbert was insoluble. Now, I'm going to give a very simplified symbolic representation of this, drawn more from the versions of the halting problem given by Chaitin than by Turing, because it's easier to explain it in a modern computing language than to explain it in terms of the states on a Turing machine tape, which is really hard to follow. Suppose there existed a program, halt pi, which will return true if program P halts on input I. In other words, this is the decision problem solution. Halt is something which answers Hilbert's decision problem. It says, given an axiomatic system P and a theorem I, will formal mechanical means cause P to halt on I? Let's then define Z, which is of the form, if halt is applied to X and X, where X is the parameter to Z, then loop forever, else halt. And that's a perfectly valid formula. What happens if we run Z, Z, Z? The two cases consider. Program Z halts on input Z, in which case halt will return true on input ZZ. If we go back, it will return true on input ZZ. Hence, program Z must loop forever on input Z. So we have a contradiction. The alternative is that the program Z loops forever on input Z. Hence, halt must return false on input Z. And hence, the program halts on input Z, which is again a contradiction. And this contradiction is brought about by the assumption that such a program that would answer the decision problem, such a program halt, could actually exist. Hence, the conclusion that halt cannot exist. And therefore, the decision problem is unsolvable. In the general case, this doesn't mean you cannot, in particular cases, take a computer program and prove its correctness. it means you cannot have a general purpose system for proving all programs correct or incorrect. It sets limits on what we can achieve by mathematical reasoning. And it indicates that there can't be a general way of seeing if arbitrary mathematical formulae follow from axioms. And therefore, it sets limits to reasoning which would not have been apparent prior to this point, and sets limits on our ability to prove the correctness of software. As I said, it doesn't prove there are no provable results in maths or no provably correct software. It means there's no general method of achieving all this. Now, I'm just going to deviate here to cover some other notes that I've prepared. Can you see the new slide? I hope so. So I've been talking about the universality of his machine. I'm going to talk now about why the digital aspect is important. So the point is, there's now a growing conception that reality itself is digital. You've seen this most explicitly in the work of people like Wolfram and Deutsch. But let's look at this in more detail. I'm quoting Turing now. That the machine is digital, however, has a more subtle significance. It means first that numbers can be represented by strings of digits that can be as long as one wishes. One can therefore work to any desired degree of accuracy. This accuracy is not obtained by more careful machining of parts, control of temperature variations and such means, but by a slight increase in the amount of equipment in the machine. To double the number of significant figures would involve increasing the amount of equipment by a factor definitely less than 2, and would also have some effect on increasing the time taken each job. This is in sharp contrast with analog machines and continuous variable machines, such as the differential analyzer, where each additional decimal digit necessitates a complete redesign of the machine and increases the cost by a factor as much as 10. He's talking about the way people did computing up to his invention, where there were machines called differential analyzers, which were used by mathematicians to solve integration of differential equations. And these basically involved rotating disks and drums, which could be, and wheels, which could be slid over the disks to perform multiplication and accumulation. And they required extraordinarily precise mechanical machining in order to get accuracy. Sorry. Turing's argument here is very pragmatic, and there has been a temptation, there's a recurring temptation to think that we can revert to analog computing and in some way outperform digital computing. I think this is almost certainly a false argument. It's based on bad philosophy. It's based on a philosophical misconception that in reality, everything is continuous. But we know this is false. Everything is actually digital or quantized. The real world is digital. The notion of the continuum arose in classical Greek geometry from the proof of the irrationality of the length of the hypotenuse of a right-angled triangle with unit sides. If one assumes, as the Greeks did, that classical geometry is a true theory of the real world, this result of Pythagoras implied that space itself must be continuously subdivisible, that there must be a possible infinity of getting things smaller, 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 and smaller. But is it even possible in principle to actually check if Pythagoras' theorem works in the real world? Could you experimentally test it? Could you experimentally test whether the hypotenuse of a right-angled triangle with unit sides was an irrational number? You can construct proofs of that using idealized concepts of lines and length in idealized Euclidean space, but is that the space that we really live in? Consider an experimental setup to test Pythagoras' theorem. I've got a figure there, which I'll show you in a moment. Suppose we've previously measured the length of the two sides of a right-angled triangle. Let's just show you the figure again. Here's the setup. It's interferometry setup. You have a laser. You've got two angled mirrors so that you have a path from there to there. You have a half-silvered mirror so that any photon has a 50% chance of following that path or following this path. And you have a detector here. And if there's an integral number of photon paths around there, you will get constructive interference. If there is a half integral number, you'll get destructive interference, and in between you'll get some mixing, but not complete destructive and or constructive. Now let's just go back to here. Whoops, sorry. Sorry, I need to zoom in here. Zooming in doesn't seem to be working. So there are all sorts of practical problems with this. Suppose we measured the A, B, and AC and established them to be an integral number of wavelengths. Can we actually measure this distance, A, C, B, A, and find that it's not an integral number of wavelengths? If you found it was, then we would have shown that root 2 was a rational number and that Pythagoras' theorem didn't hold in the real world. But there are also some practical problems to doing this. You can't simultaneously measure BC and AC because of mirror orientation. And more significantly, how do you ever set the thing up to be at right angles? The standard ways we use to set up something at right angles are on the basis that we assume Pythagoras' theorem. The standard way to construct a right angle is to use a set of sides which will meet Pythagoras' sum of squares criterion, a 3, 4, 5 triangle, for example. So it's almost impossible to see how you'd actually test this, except at cosmological scales. And at cosmological scales, we know it doesn't apply. Well, we know that the space is not such that Euclidean rules generally apply, but that doesn't mean that in the real world, is there such a thing as root 2? Is there such a thing as an irrational root 2? So, sorry, I've got to get control of this. More generally, we've got a problem that's a fundamental limit to spatial accuracy set by the Planck length, which is about 10 to the minus 35 meters, and this is going to set the fundamental limit of any analog devices. And if you come across proposals for trans-Turing computing or hypercomputing. Almost all of these are based on the illusion that real numbers are real in the ontological sense. They set up some form of calculation which makes sense if you take the Euclidean or Pythagorean idea of real numbers, but that is not evidence that it would work in the real world. Other examples of where people want to transcend Turing involve other continuum models, either solutions to Maxwell's equations under certain circumstances, or types of Newtonian mechanical computers. But if we take the post-Turing form of ontology or epistemology, you have to recognize that theories like Maxwell's equations or Newtonian mechanics are, in a sense, a software package for making predictions about reality. And they don't do anything until they're combined with some kind of computer that can do the maths that allows us to build models that mimic some part of reality. Newton's laws don't mimic reality. It's Newton's laws plus some way of performing the calculations on the observed positions of the planets, whether it was done by hand in Newton's day or was done by a computer nowadays. But like any analog model, there are limits to the accuracy of the software packages, and our software packages aren't reality itself. So you can't assume that because Newtonian mechanics says you could do something that goes beyond Turing, that implies that the real world will allow you to do that. Now, suppose we take some continuum model of mechanics, and we showed a system with computable boundary conditions has some points in the space where the parameters, let's say the parameters of the electromagnetic radiation, are uncomputable. Does this tell you that the real world can do things which go beyond what Turing says can be done? By uncomputable, I mean parameters which no Turing machine could compute the answer to. Does this mean that the real world does things that Turing machines can't do? No, what it tells you is that the software package of physical theory that you're using of the world may have a bug in it. And it's just such a bug in Maxwell's equations that led to what's called the ultraviolet catastrophe. And from this, Einstein went on to invent the quantum theory. So assuming that a certain physics formula, which is founded on continuum mathematics, gives you an answer to something, is not a safe answer or a safe assumption to make about the real world. And the conclusion I would draw is, because of quantum effects, reality is in a sense digital, and that therefore Turing computability is unlikely to ever be transcended by any analog computing device. Now, I've said that reason moved from a faculty of the soul to a formal process with Boole. With Turing, it becomes literally a mechanical process, something done by machines. What has happened here is that it is established an entirely material foundation. It's no longer something ideal, something of airy spirits. Let's look at how this applies to something practical that he did in the 1940s. How does the decision problem relate to code breaking? Well, you've probably all seen pictures of the Enigma machine, which was originally a commercial encryption machine, which was adopted by the German armed forces. And it was basically a multiple substitution process. Now, it's well known that if you use a Caesar cipher, which is just a letter substitution. It's very easy to break by frequency analysis. But what this did is every time you press the key, it used a different substitution. It changed the substitution as you went along. And this made it much harder than a Caesar code. What it has is rotors with the letters written on them and a set of contacts which go in a jumbled fashion, one-to-one, between contacts on this side and contacts on that side. And every time you press a key, the wheel rotates so that the substitution between the letters changes. You're using a different substitution on every letter. And by that, you might be able to break it. But the problem is, it was fed through 3 of these rotors in succession. So that a letter sent the letter A might send a signal which is jumbled once, jumbled 2 times, jumbled 3 times, and then jumbled another time by a fixed reflector and might give you the letter G. But the second time you pressed A, you don't get a G, you might get a C this time. So it's very hard to work out how on earth you're going to break that. It's basically, the mechanism was like an old car mileometer. Every time you pressed it, the right rotor moved by 1. When that had moved 26 times, the middle rotor moved by 1, etc. At the start of the day, you set letters on the dial there, which is the starting positions of the wheels. If you knew what these day settings were, and you have a copy of the machine, then you can decode any message. And the people who are sending the message and the people who are receiving the message have a code book which says, for the 7th of October, the code is RDK. So the person sending the message and the person receiving the message sets their machine to RDK. For another day of the year, they have a completely different set of letters. So unless you know these 3-letter codes, you can't tell what has encrypted the message. How was this breakable? Well, certain ships and weather stations sent out messages each day with a known starting sequence of letters. So Wetter für die Nacht might come out from a weather station. And this was known as a crib. Now let's look at this in terms of Turing's decision problem. The decision problem determines if axiom A leads to a theorem D. In the Turing, we can write that as D, A goes to T. In the Turing machine, both of these are numbers and both are on tape. The equivalent decryption was to decide if a setting C and a setting S and a crib C produced a ciphertext T. So you're saying, does SC generate T? And for that, you need a computer model of the Enigma machine, which he constructed. And it did parallel searches on settings until it came up with one which correctly enciphered it. And I've considerably simplified the details here. There are other things involved. There are other things involved to make sure you can do a quick mechanical check as to whether you've deciphered it. Is what's coming out sensible German or not? And that's done by statistical analysis of the frequency of the letters in the output at the end. But that can be mechanized. So what's the lasting impact of this? Well, obviously, the first is this idea of the universal digital computer. The universal machine, he says, a digital computer is a universal machine in the sense it can replace any machine in a very wide class. And in this sense, digital computers are like human workers. We are, in CapEx terms, universal robots. We can, given time and numbers, do any work. Universal robots obviously just meant, in Czech, universal workers. CapEx play, Rossum's Universal Robots, was playing in London around the time Turing wrote his paper. This universality explains the potentially huge economic impact of the digital computer and how it has transformed the world economy since he came up with the idea. Beyond that, there's the whole field of what's now AI, which sprung from suggestions by him. He argued strongly that computers can be made to learn. He argued that in principle they could think, and that in due course they would be able to converse with us in ways that are indistinguishable from conversing with a human being over a digital channel where all you can do is type in messages. On the issue of whether a machine could have feelings, he says, well, you've got no more philosophical basis to deny that a machine has feelings than you have to deny that another person has feelings, or no more reason to assert that another person has feelings than you have to potentially deny that a machine has. I would suggest that for further reading, you look at Copeland's biography of Turing and almost any of the books by Gregory Chaitin, but the Unknowable is a good introduction to these areas. So I'm going to stop sharing my screen. And I think that's 1 hour now covered, so, or almost an hour. So I'm open to people asking questions.